Welcome back to another deep dive from Peaceful Rooster Experience. Today we're going to unpack something
Oh, yeah.
that's revolutionizing the way we handle
It is.
massive amounts of data. The Tungsten Project
It's amazing.
and its impact on Apache Spark.
It's a fascinating journey, really, from bottlenecks to breakthroughs.
Exactly. But before we get into the nitty-gritty,
Right.
let's quickly set the stage for our listeners.
Yeah.
Imagine trying to analyze all the tweets sent in a day,
Oh, wow.
or the purchase history of a massive online retailer.
I see.
We're talking data sets so large, they can make your head spin.
Yeah.
That's where Apache Spark comes in. Think of it as a supercharged engine built for big data processing.
Okay.
The problem was, before the Tungsten Project,
Yeah.
Spark was running into some serious roadblocks.
You could say it had all this horsepower, but was stuck in first gear.
A perfect analogy.
Yeah.
So what were these major roadblocks holding Spark back?
Well, there were 6 key areas where Spark was facing limitations.
Okay.
First off, inefficient memory usage. Okay.
Spark was heavily reliant on the Java Virtual Machine, or JVM,
Right.
which, while great in many ways,
Yeah.
has a tendency to create a lot of garbage during processing.
I see.
That garbage requires constant cleanup,
Yeah.
a process called garbage collection, which was eating up a huge chunk of Spark's processing time.
Okay.
Think of it like having to stop every few minutes to take out the trash while you're trying to cook a gourmet meal.
Not very efficient. And how did this garbage situation impact Spark's performance in the real world?
It meant that simple tasks like analyzing customer data for targeted advertising
Right.
could take much longer than they should,
Yeah.
potentially costing businesses valuable time and opportunities.
Okay, so inefficient memory management was the first hurdle.
Yes.
What was next on the list?
The second bottleneck was Spark's row-based execution model.
Okay.
Essentially, Spark was accessing and processing data one row at a time, like reading a book word by word, instead of absorbing entire paragraphs at once.
This approach led to constant CPU cache misses,
I see.
meaning the processor was spending way too much time searching for the data it needed.
So it's like trying to find a specific fact in a textbook by reading every single line instead of using the index.
Precisely. It just wasn't an efficient way to use the CPU's resources,
Right.
especially when dealing with massive data sets.
Got it.
Yeah.
So what was the third bottleneck Spark was grappling with?
The third issue was tied to how Spark was executing its code.
Okay.
It relied on something called interpreted execution, meaning the code was essentially being translated line by line as it ran. Imagine having to stop and decipher a secret code every time you wanted to follow a recipe.
Right.
It's a slow and cumbersome process.
That sounds incredibly inefficient.
Yeah.
How did that translate into real-world limitations for Spark users?
It meant that complex data analysis tasks,
Sure.
like building recommendation algorithms or training machine learning models,
Right.
could take significantly longer, hindering data scientists and researchers in their work.
Okay, so we've got inefficient memory usage,
Right?
row-based execution,
Yes.
and interpreted execution.
Yep.
That's 3 bottlenecks down. What was the fourth one?
The fourth issue involved slow intermediate data handling.
I see.
When Spark was performing complex calculations, it was storing temporary results or intermediate data in the computer's main memory.
Right.
Now, while main memory is pretty fast,
Yeah.
it's still much slower than the CPU's internal memory, called registers.
Right.
Imagine having to write down every single calculation on a piece of paper. Instead of keeping it all in your head, it's going to slow you down.
So accessing data from main memory is like taking notes?
Yes.
While accessing data from registers is like thinking.
A great way to put it. And that difference in speed can have a major impact on overall performance.
Right.
Especially for tasks that require a lot of back and forth with the data.
This is fascinating. All right, that brings us to bottleneck number 5.
Okay.
What was it?
This one had to do with Spark missing out on some key CPU-level optimizations.
Okay.
Specifically, it wasn't taking advantage of 2 powerful techniques, CMD and loop unrolling.
Got it.
SIMD stands for single instruction, multiple data.
Okay.
And it allows the CPU to process multiple pieces of data with a single instruction.
I see.
Like using a food processor to chop multiple vegetables at once.
Okay.
Loop unrolling, on the other hand,
Yeah.
streamlines repetitive tasks by executing multiple iterations at once.
Okay.
Similar to an assembly line speeding up production.
So it's like having a team of expert chefs working in parallel instead of one chef trying to do everything by hand.
Exactly.
What kind of impact did these missing optimizations have on Spark's performance?
Without these techniques, Spark was essentially leaving a lot of the CPU's power untapped,
Right.
leading to slower processing times,
Yeah.
especially for tasks involving lots of repetition like sorting or searching through data.
Okay, so we've covered inefficient memory usage,
Yes.
row-based execution,
Right.
interpreted execution,
Right.
slow intermediate data handling,
Yep.
and no CPU-level optimization.
That's right.
That's 5 bottlenecks.
Right.
What was the last one?
The final bottleneck involved inefficient data serialization.
Okay.
Think of serialization as the process of packaging data for transport, like wrapping a gift.
Right.
Spark was using a generic packaging method
I see.
that wasn't optimized for its specific needs,
Okay.
adding unnecessary bulk and slowing down the transfer of data between different parts of the system.
This is like trying to ship a small item in a giant box filled with packing peanuts.
Exactly.
Not very efficient.
And when you're dealing with the massive data sets that Spark is designed to handle,
Right.
this inefficiency can really add up.
Right, so those are the 6 major bottlenecks that were holding Spark back.
Yes, quite a list.
Sounds like a formidable list of challenges.
Yeah.
But before we dive into how the Tungsten project tackled these roadblocks,
Okay.
let's pause for a moment and reflect on what we've learned so far.
Sounds good. So, those bottlenecks,
Yeah.
quite a challenge for Spark.
They really were.
But the Tungsten project tackled them head on.
Yes. It's time to see how they untangled that performance knot.
Right, so first, that inefficient memory management.
Right, the garbage problem.
Yeah, Tungsten addressed this by introducing off-heap memory management.
Okay.
Instead of relying solely on the JVM, Spark could now manage memory directly.
So they took memory management into their own hands.
Exactly, and this minimized those disruptive garbage collection pauses.
Wow, what kind of real-world impact did this have?
Think about a financial institution using Spark to detect fraudulent transactions in real time.
Oh, yeah.
With off-heap memory management, they could process those transactions significantly faster,
I see.
potentially saving millions by stopping fraud in its tracks.
That's a powerful example.
Yeah.
Okay, on to bottleneck number 2, row-based execution. How did Tungsten address that?
Tungsten brought in a game changer here by adopting columnar execution. Instead of processing data row by row,
Yeah.
Spark could now organize and access data in columns.
So they brought organization and efficiency to the data retrieval process.
Precise.
What kind of speed improvements did that achieve?
This optimization alone made queries run 2-5 times faster.
Wow.
A company analyzing customer behavior could now generate insights much more rapidly,
Right.
giving them a competitive edge in the market.
2 down, 4 to go. What about interpreted execution and that cumbersome code translation process? How did Tungsten tackle that one?
Right, so for this, Tungsten introduced an ingenious technique called whole stage code generation, or WSCG.
Yeah.
Instead of translating Spark's code line by line at runtime, WSCG generates optimized machine code for the entire query up front.
So they streamlined the code execution process.
Exactly.
What kind of real-world improvements did that lead to?
WSCG sped up complex operations like joins, which are crucial for combining data from different sources by a factor of 2-8x.
Wow.
This means a social media company could now analyze user interactions across different platforms much faster,
I see.
leading to more accurate trend predictions and targeted advertising.
3 bottlenecks down, 3 to go. How about that fourth one, slow intermediate data handling and the note-taking analogy?
Right, so Tungsten addressed this by utilizing the CPU's registers, which are like a high-speed scratch pad located right inside the processor. Accessing data from registers is incredibly fast, orders of magnitude faster than fetching it from main memory.
So they moved the calculations from the whiteboard to the brain.
Precisely.
What kind of real-world impact did this optimization have?
Think about a scientific research team using Spark to analyze genomic data for potential disease markers. With faster access to intermediate data, they could run complex simulations and analyses much more quickly, potentially leading to faster breakthroughs in disease prevention and treatment.
That's incredible. All right, we're down to the last 2 bottlenecks. What about those missing CPU-level optimizations? SIMD and loop unrolling.
Right. Tungsten wisely implemented both of these techniques. With SIMD, Spark could now process multiple data points with a single instruction, making operations like sorting and searching through data much faster.
I see.
And loop unrolling streamlined repetitive tasks by executing multiple iterations at once,
Got it.
further boosting efficiency.
So they supercharged Spark's processing capabilities.
They did.
What kind of real-world benefits did these optimizations unlock?
Imagine a transportation company using Spark to optimize logistics and delivery routes.
Okay.
With SimMD and loop unrolling, they could process real-time traffic data and weather patterns much faster,
I see.
leading to more efficient routes, reduced fuel consumption, and faster delivery times.
5 bottlenecks down. Now, what about the final bottleneck, inefficient data serialization and the bulky packaging problem?
All right. Tungsten replaced Spark's generic serialization method with a custom framework specifically optimized for its needs.
Okay.
Think of it like switching from standard shipping boxes to custom-fit packaging.
Okay.
You eliminate wasted space and streamline the transportation process.
So they found a way to ship data more efficiently.
Exactly.
What kind of real-world impact did this optimization have?
A media streaming platform using Spark to analyze user preferences and personalize content recommendations could now process massive amounts of viewing data much faster,
I see.
leading to more accurate suggestions and a better user experience.
It's amazing to see how each of these seemingly technical optimizations translates into tangible benefits across so many different fields. So Tungsten addressed all 6 bottlenecks, transforming Spark from a car stuck in first gear to a high-performance racing machine.
Yes, the results are quite impressive.
They are.
But before we dive into a head-to-head comparison of Spark's performance before and after Tungsten,
Okay.
let's pause for a moment and reflect on what we've learned so far.
All right, so we've seen how the Tungsten project tackled each of Spark's performance bottlenecks one by one.
Right.
But what does that look like in terms of actual performance gains?
Oh.
Can you paint a picture for us
Yeah.
of how much faster Spark became after Tungsten?
Absolutely. Let's compare Spark 1.5,
Okay.
which is before Tungsten's magic,
Right.
to Spark 3.4, where you really see the project's impact. It's like night and day.
I'm ready for the speed showdown. Let's hear it.
Okay, first, memory management.
Right.
Spark 1.5 was bogged down by garbage collection,
Yeah.
taking up a whopping 30–50% of its execution time.
Wow.
Spark 3.4 with off-heap memory management brought that down to a mere 5%.
That's huge.
It's a tenfold reduction in overhead.
Wow.
Imagine what you could do with all that extra time.
That's a huge boost in efficiency. What about the execution model? How much did columnar execution change the game?
So Spark 1.5 trudged along with row-by-row processing.
Right.
Spark 3.4, on the other hand, embraced the power of columnar execution and saw speeds increase by a factor of 2 to 5 times.
Wow.
For businesses analyzing customer data or researchers crunching scientific data,
Yeah.
this means insights arrive that much faster.
Okay, so we're seeing significant gains in speed and efficiency.
We are.
What about the code execution itself? Did WSEG really make that much of a difference?
You bet it did. Spark 1.5 relied on interpreted execution, which was like reading a recipe one word at a time.
Yeah.
Spark 3.4 with whole-stage code generation precompiled the instructions for faster, smoother execution
Okay.
and boosted the speed of complex operations like joins by 2 to 8 times.
I see.
Think about analyzing social media interactions for market trends.
Right.
Faster joins mean you can connect the dots between different data sets and discover those trends much more quickly.
So WSCG really unlocked a whole new level of performance for complex data operations.
It did.
What about the use of CPU registers for intermediate data handling? How much of a speed difference did that make?
Well, Spark 1.5 was constantly taking notes.
Right. Writing down intermediate calculations in main memory.
Yeah.
Spark 3.4, however, was thinking on its feet,
Okay.
using CPU registers for lightning-fast access to data. This led to a mind-blowing 10 to 100 times reduction in memory access latency. Imagine the possibilities for scientific simulations or real-time financial modeling with that kind of speed.
It's almost like teleporting data instead of physically moving it.
Yeah.
And finally, how did SIMD and loop unrolling impact those repetitive tasks?
Spark 1.5 was using standard Java loops,
Right.
which were like a single chef trying to cook a banquet single-handedly.
Oh, I see.
Spark 3.4 with SIMD and loop unrolling brought in a whole team of chefs working in parallel, resulting in 2 to 6 times faster sorting and hashing operations.
Wow.
Think about optimizing delivery routes in real time.
Oh, yeah.
With this kind of speed, you could respond to traffic changes and get packages delivered much more efficiently. It's incredible to see how these technical optimizations translate into real-world benefits across so many different fields.
Yeah.
So Tungsten clearly revolutionized Apache Spark.
It really did.
But its impact goes beyond just making Spark faster, doesn't it?
It does.
What's fascinating is that Tungsten's innovations have rippled out and influenced the wider big data landscape.
You're absolutely right. For example, the columnar storage format that Tungsten popularized
Right.
has become an industry standard.
I see.
Tools like Apache Arrow and Parquet, widely used today,
Yeah.
owe a lot to Tungsten's approach.
So Tungsten didn't just improve Spark. It helped shape the future of big data processing.
It did.
That's remarkable. Now, before we wrap up,
Okay.
is there a key takeaway you'd like to leave our listeners with, something to ponder beyond the technical details?
I think what's most inspiring about the Tungsten project is that it highlights the power of relentless optimization.
Right?
It shows that even mature, complex systems can be significantly improved with a deep understanding of their inner workings and a willingness to challenge the status quo.
It's a reminder that we should never settle for good enough.
Right?
And always strive for better.
Yeah.
And for those of you listening who might not be data scientists or software engineers, what lessons can you take from this deep dive into the Tungsten project? Perhaps it's a reminder that even the most complex problems can be broken down and solved with creative thinking and collaboration.
Exactly. The Tungsten project was a collaborative effort
Right.
involving developers from all over the world, working together towards a common goal.
Yeah.
And the impact of their work is felt far beyond the realm of big data, influencing countless technologies and applications that we use every day.
That's a powerful testament to the impact open source collaboration can have.
It is.
So to our listeners, keep exploring, keep learning.
Yeah.
And who knows, maybe you'll be inspired to tackle the next big performance bottleneck that's waiting to be solved.
It's been a pleasure diving deep into the Tungsten project with you.
And to our listeners, thank you for joining us on this journey into the heart of big data processing. Until next time, keep those minds curious,